if I was very strict and I said, okay, I've asked you for a kernelization algorithm and it asks you to output me an instance, so you have to output me some instance in this case, what could you do? But the instance should have size this, right? Its size should be bounded by the parameter. In this case, it's not guaranteed whether the size will be bounded by the parameter, right? But what I know here is that the instance, the input instance itself is a yes instance. So basically, so what is the property that I want? I want to output an equivalent instance of small size, right? Like, just think about it. Like, it's like how we cheat. Exactly. Just return an instance that is always true, and that's small, a trivial instance. For example, in this case, I'll output an instance where psi is a single clause, which is x1 or x2 or x3, and k is say 1. So you want to find an assignment that satisfies at least one clause. So this is always a yes instance, right? So in this case, I've output you an equivalent instance, and of course its size is small, right? So basically, if during kernelization you observe that, okay, in this case, it's always a yes instance or always a no instance, you can always create some trivial yes or no instance of constant size or of this case size and return that, okay? So for henceforth, whenever we conclude that in this case we can say yes or no, I'll just write yes or no, but for a kernelization algorithm, you can always think of some trivial instance to return. So again, note that and this is indeed a trivial kernel because we haven't really pre-processed. We just observe certain thing and we realize that if it is big, then I know it's a yes, and otherwise it's a small. The size of the input graph itself is small, and when I say small, it's bounded by the parameter. So if the parameter was small to begin with, the size will be small, okay? So this is one example of a trivial kernel. Now we'll see another example, and I hope you guys will be able to guess it because Sunil has already refreshed the vocabulary which is needed for this. So let's try to solve the independent set problem, but not on general graphs, on planar graphs. And there's a reason that I'm not doing it for general graphs. One could be that the proof is very hard, but it's not that the proof is very hard. It's because that if I was able to give you a kernel for independent set on general graphs, I would earn $1 million or probably be shooted because people don't believe such a kernel would exist for this problem. I mean, we'll see some lower bounds in the last class, and let's see how much we will be able to cover it there, but that's for fact. So what we are doing right now is we are looking at this problem called planar, let's say, independent set. So what's an input? The input is a planar graph, okay? And so the input is a planar graph, and again, it's always a positive integer k, okay? And the output is, the algorithm outputs yes if G has an independent set of size k and no otherwise. So it's the standard independent set problem, but the input is now a planar graph, okay? So again, the parameter here is k, okay? So let's see, what can you say for independent set? See, again, the kind of ideas that you want to come up with is, okay, if suppose we can say that, okay, a planar graph always has this, at least this much independent set, then we can always return yes, and otherwise something of this sort. Okay, do we have some lower bound on the size of an independent set in a planar graph? Like here we had a lower bound that any assignment will satisfy at least m/2 clauses, right? So if you say that, okay, any independent set in planar graphs will have size at least something, then probably we can try to use that fact. Sorry? You've learned
maximum chromatin number in
is what?
6.
Yes.
So we can do that.
Okay, so let's go by that. So this is an easy proof, right? That I think you've learned about planar graphs, right? Lavanya taught you. Have you guys seen a proof of like the chromatic number of a planar graph is 6? It's easy. Did you see it in the class? Yes or no? Okay. So let me just tell you, and I'll briefly tell you the proof of this also, probably later. So in a planar graph, this is a fact, that the chromatic, if G is a planar graph, then the chromatic number of G is at most 6. Actually, it's at most 4. But the proof of it, it's non-trivial. But the proof of 6 is what you can see easily. So it doesn't matter what we choose. So suppose I tell you this, then you were saying something. Then what can we say? Then do we have any lower bound on the size of the independent set? So okay, what does it mean that a graph has chromatic number 6, as Sunil was just teaching you? How can you alternatively look at a graph with chromatic number 6? If the chromatic number of the graph is 6, so look at this coloring using 6 colors and look at each color class. So this is all the vertices that get color 1, all the vertices that get color 2, and so on, all the vertices that get color 6. Each of this color class is an independent set, right? Then now what can you say about the size of, can we say that such a graph will always have an independent set of certain size? Okay, n by 6 is okay, right? Pigeonholing. So there are n vertices. They've been divided into 6 classes. Of course, one of the class has to have at least n by 6 vertices, and each color class is an independent set. So any planar graph we know has independent set in any planar graph. If G is a planar graph, then G always have an independent set of size at least n by 6. Right? Now this is basically an analogous observation to this, and after that what we will do, the same sort of strategy, what will you do? What is less than n by 6? K. Right. So if I'll just go check K, if K is at most n by 6, so if you're looking, if your goal is to come up with an independent set whose size is at most n by 6, then I know I can always give you an independent set of this much size. So in this case, I can always say, otherwise, K is greater than n by 6 or n is 6K, right? And this is of course a kernel, but this only bounds the number of vertices. Can you bound the number of edges? Yes. So if in a planar graph, you always have this bound that m is at most 3n minus 6. So if n, can you see this? No. So what we had was independent set of the graph is at least n by 6. From there we said that okay, if K was at most n by 6, then say yes. Otherwise, K is greater than n by 6, that means n is at most 6K. And in planar graphs, basically you have this bound that m, the number of edges in a planar graph, is always at most 3n by 6. So this gives us a bound on the number of edges also. So again, this is a trivial kernel. We don't really have to do anything. So while we are here, I would want to ask you a question. So how did we come up with this independent set? We said, okay, look at the 6 coloring of the graph, and look at the 6 coloring of the graph and look at the maximum size of the independent set, and that will have size at least n by 6. Okay, but when I'm designing a kernel, do I really have to go look at the coloring of the graph? Like, okay, or in other words, what is this polynomial time algorithm doing? What will this polynomial time algorithm do? Will it go first compute the coloring of the graph and then do something, or can it avoid computing the coloring of the graph and just conclude something?
Looking at the
Exactly the point. So see, we looked at the coloring for our like to observe that this is always the case, right? No matter what planar graph you give me, this is always the case. That's all we use the coloring for. The pre-processing algorithm will not go compute the coloring. It will just go check if k is at most n by 6, it will say yes. Otherwise, it will output the same instance. Because this is for a fact, like, so this is the difference between an existential argument and a constructive argument. All we want to say is that there is always an independent set of this much size. I'm not asking you to give me an independent set of that much size. There is always this, so hence I can conclude this. F of p, yes, I agree. So what am I returning? I look at two cases. Either k is this or it is this. If it is this, I return a trivial yes instance. So what could be a trivial yes instance? Just take a graph on one vertex, it is planar, and ask if it has an independent set of size 1. It has 1. So that's a trivial yes instance. So in this case, I'll return that instance. In this case, what am I returning? The same instance. And we just argued that the original instance itself has size bounded by a function of k. And the same instance is of course an equivalent instance because I'm returning the same instance, right? So I mean this is exactly what we did in max 3 sat, right? So it just turns out that if the parameter, see, try to look at intuitively what is happening. What is happening is we are saying if the parameter value was smaller than the size of the input, if it was much smaller, in that case we know, so basically what is this saying? In other words, it's saying that the graph has a lot of vertices and the parameter is very small, okay? So in that case, if I had to come up with an equivalent graph, like I had to throw away a lot of vertices to get to an equivalent graph which has size bounded by this k, right? But this observation saves me to do all this pre-processing. This observation is just saying, okay, if this is the case, then you don't even have to look at the graph. You know it's a yes. So I just saved that there. This thing is nothing but, what is this saying? It's saying if the parameter is not small, then the parameter is big. Big as in the parameter is as big as the size of the graph almost. So or in other words, the graph size is bounded by the parameter because the parameter is so large. So we can as well return the whole graph. So note that of course in this case, if k was a big number, then what we are returning is a big number. But again, as we said in parameterized algorithms, our goal is to return, like in kernelization, our goal is to return an instance which has size bounded by the parameter. Now depending upon what parameter you give in the input instance, this will either be it'll either be a really small kernel or just a small kernel to say. Right? I mean that's what we saw in the morning when we gave a 2 power x into polynomial time algorithm. We said for instances that have small x values, you actually get a polynomial algorithm. But there might be instances that come with large x values. All I know is the running time is 2 power x into polynomial in n. Like it's bad, we know that, but I mean, and we can't hope to get good algorithms for all the instances because we're working with NP-hard problems. So now we'll quickly do the vertex covered kernel as we promised. So there we actually have to design some pre-processing, some real pre-processing, and get a kernel. So we have this vertex cover problem. Again, we all know the problem. Still write it. Input is a graph G and an integer k. The parameter will be k. And output is yes if G has at most k vertices such that all edges of G, let's say k vertices S, such that all edges of G have at least one endpoint in S and no otherwise. Okay. So definitely, as we saw in the morning, if there are any isolated vertices in the graph, we can definitely delete them. Right? Or in other words, let me just say, suppose V is a vertex in the graph such that degree of V is 0. So that means it's an isolated vertex in the graph. Then my claim is, what does an instance of vertex cover look like? It's of the form G, K. then my claim is that g comma k is equivalent to g minus v comma k. In other words, if this had a solution of size k, then will this have a solution of size k? Like whatever is the solution here, isn't that the solution here also? Similarly, if I give you a solution here of k size, isn't that a solution here? So these are equivalent instances, right? But note that if I just do this, I have just proved this property that they are equivalent instances. I have not really proved this. Maybe after deletion of this isolated vertex, it's not clear why the size of G should be bounded by the parameter, right? So usually when we do kernelization, to achieve this kind of a bound, what we usually do is, we call such a thing a reduction rule, okay? What is a reduction rule? It takes an instance of a problem and outputs an equivalent instance of the same problem. So basically it has only this first property, not the second property, okay? So what we do is, we design a set of reduction rules and we just apply them one by one, okay? And note that suppose I have one reduction rule that takes an instance and returns an equivalent instance. Now suppose I have another reduction rule that takes one instance and returns an equivalent instance. And if I just apply the rules one after the another, in the sense that suppose I applied this rule first, I found a vertex of degree 0. I took this instance, returned this instance, right? Now suppose I find another vertex again of degree 0, I'll take this instance and do this. So when I'm again going to apply this reduction rule, on which instance will I apply this reduction rule? The already reduced instance, right? So basically, see, every time once we have reduced the instance, we can forget about the original instance and treat this as a fresh instance, right? And because this equivalence relation is transitive, in the sense if this is equivalent to this, and if I further reduce this to another instance, this will be equivalent to this. In particular, this will be equivalent to this, right? So I can always forget about like the initial thing and just focus on this is called the reduced instance of this. So all I'm trying to say is, if I have a set of reduction rules, and what is a reduction rule? It takes an instance, gives outputs an equivalent instance. If I have a set of reduction rules and I'm able to say that, okay, you keep on applying these reduction rules. So when I say keep on applying, take an input, give an equivalent input. Then look at this input, apply another reduction rule over this, it gives another input. I keep on applying this reduction rule and stop when you can no longer apply it. For example, when can you no longer apply it? When there is no vertex of degree 0, right? So suppose I have a set of reduction rules, I keep on applying it until I can. And now look at the instance that I get eventually. So the instance that I get eventually, as in on this instance, none of these reduction rules are applicable. If suppose I can argue that now this instance has this size bound, then also I'm done. Modulo each reduction rules runs in polynomial time, because I want a polynomial time algorithm, and the number of times I apply reduction rules is polynomial, right? Because I want a polynomial time preprocessing algorithm. I'll apply the reduction rule one at a time until it's possible. So I should not be applying the reduction rule in loops. It should stop after polynomial many steps. So basically, most of the kernelization algorithms will reduce to designing some set of reduction rules with a property that we'll keep on applying this reduction rules whenever it's possible, and we apply the reduction rules only polynomial many times, and each reduction rule is runs in polynomial time. For example, this reduction rule clearly runs in polynomial time. All it has to do is search if there is a vertex of degree 0 and then delete it from the graph, right? So we design reduction rules, and then once we have applied all the reduction rules, if we argue that, okay, if you have an instance where none of these reduction rules are applicable, then its size is this, then also we are happy, right? And this is what we're going to do for vertex cover, for example. So we apply this reduction rule whenever it's possible. Get a degree 0 vertex, delete it. So we say a reduction rule is safe if, like, it takes as input this instance, outputs this. It's safe when these two instances are equivalent. So this is the terminology that's used in literature. So it might slip from my tongue anytime. So when I say reduction rule is safe, it's just that this instance is equivalent to this instance. Okay. So definitely this reduction rule is safe for vertex cover. This instance is equivalent. So, but once I have exhaustively applied this reduction rule, let's see if we can bound the size of the resulting instance, and if not, we'll try to capture what is the structure that making its size unreducible, like what is it that's making its size large, and then we'll go back and try to see if we can reduce this, we can design a reduction rule that finds this structure in the graph and somehow makes it short, something like that.